All right. Well, why don't we get going? I'll write around this for a minute in case anybody shows up late, and then at some point I will need the space. Okay. So what we were finishing up last time. So at the end, we were looking at the sort of quoted remark was sort of ITT is a theory of sets, and we got to two. So we showed that all of the basic constructs of type theory of ITT preserve, or are, if they don't preserve, the is-set relationship. And remember that we define is-set A to mean, by definition, we can say that for every x and y in A, and any two proofs that they're equal, x and y are equal, that there's a proof that in the iterated identity type that P and Q are equal. Okay, and in a little while we're going to have a way to abbreviate this a little bit. That will write it a little shortly. So there's up to higher homotopy at most one proof of equality of any two elements. That's the criterion for being a set. Okay, so we said that all the basic constructs preserve a set, and then we said in a retrospective way, like this is one of those things where when you look back you can say it a different way than you might have said it originally, is you could say that the universe U is sort of rigged to be a set, and it's a set of codes. So what happens is, like if you look in the NPS reference, as I mentioned last time, they'll have a code. I think they write it with a dot or something, but anyway, a code, this will be in U, and then you have a decoder, and there are different notations. I've forgotten what they use, and they say that T of nat dot is probably definitionally equal to nat, or things equivalent to that. And you get the idea. These are sort of abstract syntax trees for types, or notations for types. Those form a set. They're inductively defined. They're morally, it could have been the natural numbers if you wanted to be kind of perverse about it and code everything up as numbers. And you just give these trees and you say how to decode them, and that's it. So it is a set. All right. It's an inductively defined set. And it has the characteristic, though, that the codes have a finer notion of equivalence than you might like, and that's like where everything comes up a little bit. We'll mention in a moment, but you just have to remember that equality in U means equality of codes because it's a set of codes, and so you just have syntax trees, and you do that. Okay, so that ends up being a set, and then the thing I left hanging, which I want to do now, is that id A, mn, let me get my notation, or call it xy, all right, is a set if A is a set. Okay, and this is an example of something that it's fair. The argument is easy. There's nothing really complicated going on, but it's really easy to get confused. So I'll probably get confused. You'll start to see why, because we start having multiple iterations of the identity type, and pretty soon you forget where you are anymore. So don't mind me if I mess this up, but I'll do my best. Okay, so here's the idea. So I want to show that this is a set. Okay, so that's what we have around here. Okay. All right. Let's see. So the idea is if A is a set, then IDA is a set. Okay. So you'll see now shortly what's going on. So what is our assumption? All right. So our assumption is that A is a set. So I have some function which I called H, which is of this type. But let me write it down to put it on this board to keep it in front of your eye. Okay. This is where this stuff gets confused. This is the part that starts getting confusing. Okay, so you say that you assume that you have a witness, right? Because we're in a proof relevant environment. So we have a witness, which is a function, a mapping with this type, that will tell us if you give it an x and a y and a p and a q, will give you evidence that p is equal to q because that's because A is a set. So assume is set A, which is to say we have that H. So that's what we're doing here, okay? And then what we want to do, all right, is we want to show that the identity is a set. So we want to show, right, is set IDA, okay, XY, which is, okay, which we're going to proceed as follows, okay? So what we're going to do, so what do we do? So I wrote it this way, so let me stick with my notes. Okay, so I assume that U and V are in A, right? That R and S are in IDA XY. And now I have to have two additional things. Alpha and beta is a proof of equality XY between R and S. That's what I assume, because you see everything's now up one level, so the A is the IDA, so this really plays the role of the X and the Y. These play the role of the P and the Q. I need the U and the V because I need to be able to say what the types of R and S are. So these are, oh, so where did the U and V come from? Oh, I was writing it, oh, I'm sorry, yeah, okay. It's best if I write my notes, follow my notes, because I'm almost certain to get this confused anyway. Okay, so let me try to be careful with that. Okay, and then what do I need to show? And then you'll see, right? And now it gets completely insane. Okay, so I have to write, so ID, okay, you see what happens to you. Okay, I'm going to stop writing the subscripts. On the other hand, as you saw in a note I circulated last week, when I stopped writing the subscripts because it was getting too heavy, the first thing I did was make a mistake involving the subscripts. So I don't know what to do, all right? It gets very confusing. Okay, at this point, you start to get like a white knuckle experience because it's hard to imagine anymore what the hell we're doing. So we have two paths between two elements, okay? So picture it how you like. All right, good luck with it. So, all right, so turns out that what you can do is we can specialize. It's convenient to specialize the hypothesis H, okay, in the following manner. You just specialize it to the particular scenario, which is U, V, R, and we'll have Q. Okay, so if you work out what that is, then, if I didn't make any mistakes, this is the type of H prime is pi q in id a u v, right? Id a u v, r and q. I hope I did that right. Okay, because I plugged in the R and the Q here, okay, so I have that. And where did I get the R from? The R and the S and the U and the V, and assuming I didn't transcribe something wrong, that should make sense, okay? So we're sort of we're focusing on one point, which is dangling. In other words, I'm fixing the U and the V and the R, and I'm looking at the Q, okay, and that's what my H prime is all about. And so now here comes the move that is both like saves your sanity and also comes up a lot, okay? Which is that we're going to exploit, so the idea is we're going to exploit the functoriality of H prime. Okay, or you could, the dependent case is often called the naturality. Okay, but the idea is this, right? So H prime is a function, okay, so with this type, pi. So it means that vertically, if I give you a Q being equal to some Q prime, let's see what I end up doing here, just to get my notation right. So well, let me just draw a picture. If I apply it in the sense of one dimension up using AppD, the action on paths. The action on path in Q will induce a path in here between the resulting types here, each of which the endpoints are of this type. So it will give me a path that has this crazy iterated identity type, okay? Because a path in here will give me, when given a path in here, H prime of the action of H prime on that path, the functorial action of H prime on that path, will give me a path between H prime of the endpoints, okay, which will end up being of this, where is it, this crazy type. Okay, so that's how we're going to inhabit that type. So we're going to do it. So let's watch how that works. That's the best thing I can tell you. Okay, is what we're going to do. So what we know is, if you take that dependent form of app, this kind of naturality witness, what is its type? Well, you have to. I'll write it all out. To write it out, it says, well, you give me two endpoints in ID, A, U, V. Okay, right, that's what that is going on here. And you give me, I called it gamma here because I was using Greek letters at that level of the hierarchy. So you give me right, that's what is going on here. Then what do I get out? What I get out is, as I just mentioned a moment ago, you get out this completely insane thing. Okay, so you have like this, and this is R and Q, and it's in the type, what I write, gamma star, the transport of H prime of Q and H prime of Q prime. Okay, that's what we get here. Okay, so this should have been the gamma star goes here, and something didn't feel right. Yeah, so that seems right. Yeah, good. So this is the path over. In other words, this is what we sometimes wrote. H prime of Q is equal relative to gamma to H prime of Q prime in the appropriate thing, which I'm not going to write down there. Okay, in the appropriate family of types. So in other words, it's a path over scenario. Move this guy over to the right fiber, to the proper fiber, and then compare it. There's a comparison between what you moved over and this guy. And so that's the leftist way. That's the leftist notation for path over. There's of course a rightist notation, which I would never use, for path overs, or you can have a symmetric version of path over. Okay, so that's the idea. Okay, so that's where we are. Okay, so now what do we know? So we have available to us particular paths. So we can look at what is app DH, okay, H prime, excuse me. Did I say that? Yeah, I did say that right. Okay, so what is app DH prime of RS and alpha? Okay, well, that's going to be, if you work it out, and if I did it right, and I'm going to stop writing the iterated subscripts because they become insane. They become like that, right? Because again, this is the leftist notation for path over, right? So if I give you this alpha, if I'm taking the functorial action of H prime, with respect to alpha is what's going on here, then you move this guy into the fiber over that same fiber as this guy and you compare them. Okay? So we're written like that. So it's saying that, so if this is the identity type, so these two things are equal. Okay? And if you do, then the alpha is what's given over here, by the way, right? Those are my assumptions. Okay? And similarly, if I do HP, RS, and beta, then I get the same sort of thing. Stop me if I get confused and something isn't making sense. But I think that's okay. I tried to write everything out carefully. Okay, so we get those two facts. So in particular, we get that. So therefore, in particular, we get those two things. All right? So we can conclude, therefore, that there's some element, which I'm not going to write down, because what's happening is you have this guy is equal to H prime of S, and this guy is equal to H prime of S. So with appropriate symmetry and transitivity, which I could write down, but I won't write down here, okay, I can get an element of the identity of alpha star H prime of R and beta star of H prime of R. Okay, by using appropriate symmetry and transitivity. Okay, good? Yes?
It's just a small thing, but in the type on the third line there you give, is it RQ or RQ prime?
It might be RQ prime. Let me look what I wrote. What I wrote is RQ, but it's actually going to be probably RQ prime. Somebody should check that. I'm bound to make a mistake here, so double check that to make sure that's right.
It just looks like you're moving over.
Because I'm moving it over to fiber over Q prime, yeah. So I probably should have, what I actually wrote is Q, but it could be I made a mistake. Okay, so check that. Okay, so now we have these two things, and now we do something else which I mentioned to you last week, which is what we're doing is we're doing a transport in an identity type, because if you look at H prime of R, the type of H prime over here, it emits something in an identity type. So we know, and alpha is a path in the thing that it's fibered over with between R and S, as we've written here. So we know something about the action of the transport is the point, okay? So what this is telling us is that, again, we can get something in, all right? This is given by post-composition. Written like that. And this is H prime of R dot beta, because you can look up the meaning of transport in an identity type, and you'll remember last week I said the identity types behave like HOMs. They have their actions, in this case the action is, in this example instance that I'm doing, that this transport property is given by post-composition. Okay, so now, so if we write this out in logical notation, all right, then you will like instantly see what is going on here. Because remember, what I'm trying to do is show that, the idea is I'm going to show essentially alpha equals beta in the appropriate sense of equality. That's what I need to show. Okay, so you can kind of see over here, so what do I have? Let's just write it out. What do I have? Let's write it in logical notation because it's a little easier to see it. We know that H prime of R dot alpha is equal to H prime of R dot beta. And we know this lands in an identity type, or it lands in a type, and all the types have a groupoid structure, right? So this is a path in a type, right? So it has an inverse, all right? So I can multiply by its inverse, which we always have, which that was a previous discussion. Or if you like to say it that way, I can divide by H of R, H prime of R, on both sides. And of course, these cancel, and we get that alpha is equal to beta. And everything has to be checked in what type did I mean that, okay? So the groupoid structure, the point of a group, you might say, is that it has a cancellation law, right? All right, if you know x times y is equal to x times y prime, then y is equal to y prime. I can cancel the x because I can divide by it, because that's what groups give you. And a groupoid is you know, a generalized group, as we discussed before. So I'm allowed to cancel. So once I know that this is equal to that, which came from the fact that we know how transport works, then I just cancel the left-hand side. Of course, later I just cross them out because I'm used to working in that structure, and I get that alpha is equal to beta. But officially what's going on is I'm exploiting the groupoid structure to divide both sides by H of R and then calculate those. And this is all up to higher homotopy. So what's going to happen is, what I'm suppressing here because it becomes too painful, I'm not really writing out exactly the proof term, right? I really should be writing out the calculation that does that, right? So there's a calculation that says, you know, I can take this guy and multiply both sides by this guy. That will be a proof term, okay? And then there's a calculation that says I have congruence, and I have the fact from the groupoid structure that this is up to higher homotopy, the reflexivity. So these are both reflexivities. You imply the congruence, and then reflexivity times anything is alpha, so you apply that rule. Reflex anything times beta, you apply that rule, and at the end you're going to get a big fat thing, okay? All right, which I have not written out. But using myself as an object lesson, if you don't write them out, it's really fertile ground for making mistakes. So although I didn't write it out, and I do believe I'm right here, but this is the spot where you could easily sort of make a mistake. You want to be careful. And the reason is, like in the case that I mentioned to you on the piazza, I had to prove some equation. Who knows? I don't even remember what it was, but I had to prove some equation, okay, and some x here, b, and I was saying, well, if all I have to do is show that that's inhabited, then one option is to show that this type is equal in the universe to some other type, And so what I was doing is I was suppressing the x. I was saying this is equal to that, and therefore if I have an inhabitant of this, then I can transport it and get an inhabitant of that, and I'm cool. That was the outline of my argument in that note I circulated and that I mentioned on the piazza. But the problem was that I wasn't writing the x's, so I'm just like warning you, all right? So the problem is I wasn't writing the x's, and this is an x and this is an x prime. And so the problem is you don't get to change the type in which you're working without also changing the terms. Okay, that's where the problem came in. And then the whole thing got such a colossal mess that, to be honest, I'm not sure whether it works or it doesn't. Okay. All right. The idea was nice as long as I could ignore the details. You see, that was the point. I was just saying, look, A is A prime, B is B prime, because if you look at it, you can see there's some cancellations and stuff that go on in there. So I have A is A prime, B is B prime. Therefore, anything in here can be transported along the identity family. And transported so I get an element of here, and then I don't dirty my hands and I don't figure out what's going on. But if you actually work it out, I would have had to worry about the transports that are implicit in x being equal to x prime, which would affect what these things look like. And then when it affects what these things look like, it's no longer clear that I get what I wanted actually. And then I got like discouraged. So it might work, I don't know. So the cheap thing to say was, well, if everything in sight is a set, it's got to work, because then the path involved has to be reflexivity up to higher homotopy, and the action is the identity, so I'm home and dry. So it works for sets. So it works for sets. And my actual intuition arose from like my experience with New Pearl, and I was thinking kind of like New Pearl. And so I thought everything's a set. Oh, everything's great. I don't have to worry about it. But if things are not sets, then it's messy. And it could be that idea can be salvaged with enough effort, but actually at least for a couple of days I gave up for a while because it got too complicated. But the reason I bring that up is because, okay, maybe it's me, but it could happen to you. Okay? If you start suppressing the subscripts on the equalities, there's an opportunity to screw it up. Okay, so I would suggest being careful. Of course, in the end, this is why we have machine-checked proofs, right? So that's what I get for writing it out by hand. Okay, so if I had done it with Agda or something, then I would have caught it earlier. So there's some value in that. Okay, so that's the argument. So all of that with this crazy iterated identity types was proving that this IDA is a set if A is a set. And at that point, I've then verified that according to my definition for the purposes of our class of what ITT is, I proved that ITT is a theory of sets. And ETT is a strict theory of sets, because what it does is remember, ETT in my definition is just ITT plus uniqueness of identity proofs, which really just says everything's a set, okay, plus what is called axiom K, which says all the loops are reflexivity, okay? So that's usually what is called ETT. And so if ITT is already a set theory in the definition I gave, then adding these axioms only makes it more set-like. It doesn't destroy any of those arguments. And so ETT is also a set theory. Okay, and so that's the idea there. Okay, so I mentioned last time. So the consequences is now, from the perspective of the higher dimensional type theory, we can now see what was going on there. Okay, because as I mentioned many times, if you're working in sets, ETT is a much better way to go than ITT. Okay? If you're not going to exploit the higher dimensional structure, there isn't, in my mind anyway, much point in mucking about with all the transports and stuff that in the end are only ever reflexivities anyway. Okay? So it doesn't seem to be, it's just a very tedious way to go. So one can say then that ITT, with the development of the understanding of the role of the higher dimensions, one can now say that ITT has been vindicated in a way by saying, well, there is an awful lot of bureaucracy there, but we can at least get something for it. Okay, and that's good. So that actually makes everyone feel happier, right? So remember that hot, right? We say. So the thing that's good about it is we define hot to be ITT also plus, but plus like univalence axiom, plus function extensionality. Well, actually, I haven't proved this to you yet, but this implies that. But right now, we'll just say plus function extensionality and plus higher inductive types, of which an example I gave was the interval, okay, which also implied higher function extensionality. So one might say it's UA plus hits. Once you actually understand all the implications of doing that, then you don't need to mention function extensionality. And then that at least is making use of the higher dimensional structure in a interesting way, okay, in order to do, for example, to do some homotopy theory. So that's what's going on here. So a way of seeing this is that to the extent that one can do homotopy theory inside of type theory, which seems to be substantial, then what you can do is you can say that you can realize that homotopy theory can be thought of as a branch of logic, even though its origins were, well, analysis via topology, right? That was originally how it got, I think, how historically it got invented. You could really see it in a retrospective kind of way as an inevitable outcome of a foundational analysis of mathematics that, at least as long as you believe that ITT is something worth looking at, if you have constructivist tendencies, then you look at ITT, and then I think eventually one would have noticed that there is this higher dimensional structure there in low that really is talking about paths in a space, and that's just what those homotopy theorist guys do. So you can see that it's really just, it's a kind of logic-based way of arriving at homotopy theory. Now that's the kind of thing that makes me, gives me goosebumps a little bit, because I think I might have told you before, when I was in graduate school, my housemate was a homotopy theorist, and I was learning type theory, and I was trying to tell him about constructivism and type theory and how great it was, and he thought I was bonkers, okay, only philosophy nut jobs think constructivity has any merit whatsoever. And he would tell me about homotopy theory, and I would be like, it's amazingly cool, but it's so far beyond the horizon, I'll probably never get anywhere near that. And then, lo, 30 years later, we realized that we were talking about the same damn thing. So I wrote to him, and I sent him a copy of the book, and I said, you know, John, if we were only a little smarter, we could have been famous. So, but we didn't realize at the time that that's what was going on. So it's kind of an amusing thing. But I still think it's kind of cool that you can think of that subject, which sort of has kind of geometric and topological origins, ends up being just as well viewed as a further development of ideas in logic. That's neat. Okay, so now I want to say one of the motivations for this discussion here is, what I want to say is that ITT plus univalence is not a set theory. That is, not all types are sets. So what I mean by that is, not all types are sets. Sets, I mean, and everything I'm saying here is meant in the homotopical sense of the word set, okay? That's another thing, that the term, I mentioned before the terminology. I'm going to compound the terminological friction in a moment. But I remember when Vladimir first visited a few years ago, when we were at dinner, and he said to me, he says, you know, it's an open problem whether the natural numbers form a set. And I was looking at him like, holy Jesus, here I thought it was an axiom of set theory. So, but what he meant was, homotopically was a set. That is, in the set that I'm describing. And at that moment in the development, it hadn't been proved yet that the natural numbers form a set. But I mean, I have to say, I was like dumbfounded by that remark. I thought, boy, I'm really stupid. I'll just keep my mouth shut. I don't know what he's saying. And then that's what it was about. So the terminology can be confusing. So this is what I mean, is that not all types are sets. And guess which type isn't a set? Okay, well, in particular, it's the universe. U is, well, it's going to be a groupoid, a proper groupoid. In general, not a set. It's not going to have, in other words, there's going to be non-trivial paths between elements. So what does it mean to not be a set? Well, never mind that it's U. It means that I've got 2 points in that set, and I have 2 paths between them, which are proofs that they're equal, so let's call those P and Q. And these are, to use Freyd's notation, the punctured notation. Peter Freyd introduced this notation to indicate that there is not a cell there, okay? So that's like a little, like, you know what I mean, like a hole in the cellophane, you know, there's a little puncture. Okay, so Freyd used that notation, well, whatever notation. So the point is that there is no cell mediating between P and Q, okay? So they are distinct. So that's what it means to be not a set. That's when I say that, I can find, well, let's give them names, X and Y. I can find X and Y and paths which relate them, which are known not to be equal. So how am I going to do that? Well, I'm going to use univalence. So the thing in question is going to be the universe. And what am I going to do? What am I going to exploit? I'm going to take 2, which by definition is 1 plus 1. Don't tell anyone I said that. Okay, so you have 2 is 1 plus 1 on both sides, by which I mean the sum of 1 and 1, yes? Okay. All right, and so I'm going to have 2. And I'm going to try to exhibit 2 paths that are different between 2 and 2. Right? Because remember, I'm working in U. So the A in question, you know, this would be A is not a set. This would be the scenario with A. These are in id A, right? Okay, so we're working in A. So now I'm working in, this is all taking place in U. So we know that 2 is in U and because it's closed under sums, okay? So we define that. But what are the paths in U? Well, remember, univalence tells us, right, that the paths in U are equivalent to the equivalences between the endpoints. Okay, we talked about that before. And we said there's a map this way that takes any path and turns it into an equivalence. And the univalence axiom goes this way. So this is definable. I'll just write it as D. Okay, so there's univalence. So this is path to id to equiv, I think it's called in the book maybe. Okay, take an identity, an identification, a path, whatever word you like to use. Take an identification and turn it into an equivalence. Univalence that's not definable, because left to right just says if you have a path, maybe the only path you have is reflexivity, and of course you can turn that into an equivalence, which would be the identity equivalence, right? So whatever paths you have can always be turned into equivalences. That's kind of, quotes, obvious, okay? But the other way around is a comprehension principle. It says there exist certain paths that are given by equivalences. Okay, so this guy is a comprehension principle, and that's like characteristic of foundational studies, right? When you're looking at foundational studies in logic, you know, the big thing typically is, in one disguise or another, you're claiming a comprehension principle, taken loosely, means you claim that certain entities, like certain sets, exist. Okay, and you just postulate them. So the most blatant one in some respects in ordinary set theory is the axiom of infinity just says the set of natural numbers exists. There's no justification for this fact. It's an axiom of set theory. So it's a comprehension principle. You just say that exists. It's the first inaccessible cardinal. Okay, because prior to introducing it, you can't make it. Okay, you have only hereditarily finite sets up to that point. So foundational studies tend to be like that. So this is a comprehension principle that says the collection of equivalences can be comprehended as the elements of a type. You see? That's what's happening. Namely, the path space of the universe. Okay, so that's a way to think about it. So that comes up pretty often. Okay, so now what I'm going to do is to create these paths, I'm going to use UA of something. Right? Because UA is the thing that creates paths in the universe. And the only one, prior to UA, the only one I know exists is reflexivity. So clearly I'm not going to be able to use, I could maybe use reflexivity, actually I'm going to, but I need to make paths out of something, and the scenario is set up in order to exploit univalence. Okay? So I'm going to use univalence. Okay? So can you think of, so what does univalence say? Well, 2, as it happens, is a set. So you can rely on like really, fundamental intuitions that you have. So an equivalence between sets is a bijection, right? So Can anybody think of two bijections between 2 and 2? Yes, probably you can. One is the identity, which doesn't do anything, and the other one is negation, which I'll write not, which swaps true and false, right? Okay? And it and not are different. It is different from not, okay, as maps from 2 to 2, because of function extensionality. When applied to something in 2, you can show that they're different. So it of true is true, not of true is false. Okay, so you can check that. So you can do that. So these two paths are going to be distinct. So I have two distinct paths. And now the idea is this. Okay, so we have not. So we have those are like two paths in question that I'm going to claim are different. So let's show how we do that. Okay, so let's look at UA of not. So first of all, you have to believe that not is an equivalence. So you have to check that. That's what I said about it being a bijection. So not is an equivalence between 2 and 2. You have to check that. Okay, so therefore UA of not is a path. So that's what we're going to do. All right, and now we have this other thing, which is really UA of ID. So we have this other thing, which is reflexivity at 2 of true. That's a proof, right, that true, whatever, I don't remember what notation I use, but anyway, true equals true, okay, that I have that. But you see, I can think of this as a family of types. I can think of this as an instance of a family of types in that position. So the UA of not tells me what I can get out of this is true is equal to false. So by transport, I can say transport of this guy is a proof involving UA of not that false is equal to true, and that can be refuted. Okay? And so I can get from there that something is in 0, and that's the contradiction I wanted. Okay? To show you that something is not a set. Okay? So that's the picture. So the idea is that you have a family of types. You can think of this as a fix one of the endpoints. I happen to fix that endpoint. Fix one of the endpoints. Think of it as a family of types over 2. You have a path now between true and false given by the univalence, what this is doing. And then what you do is you do transport along that path. And so since reflexivity is in true and true, then something or other, transport of reflexivity is in false equals true. And that's 0. So what I've done is I've essentially proved not is set of U, which by definition is set of U arrow 0. So that's what I actually did. I showed that is set of U arrow 0 is inhabited. Okay, that's the argument. Okay, so that's what I'm doing, and that's the picture. Okay, so that's officially what I did. Okay, so I can internally refute. So the point is, it's not a meta argument, right? I'm internally refuting the premise that the universe is a set when you have univalence. You have to have univalence. The whole thing depended on having univalence around, okay? Without that, of course, it actually is a set because it would only be reflexivity, so you're going to be a set. So it's only because of univalence. So univalence is a comprehension principle. The comprehension principle pumps up the structure of paths in here in such a way that we have non-trivial paths, okay, the distinct paths between elements in this universe, and then yeah, anyway, that's what I wanted to say. So, yeah, okay. Okay, so that's telling us now that when that's the beginnings of telling us that when I have homotopy type theory, that I get something more than a set theory. So that's where I am now. Okay, so now we're in a position of saying this thing we've been discussing is I can now say is for sure not a vacuous thing. See, the point I'm making is that, for example, the proof of the fact that the types in ITT form a groupoid is all perfectly valid. You get the groupoid structure, but it's sort of like counting angels on the head of a pin because it's a groupoid structure, it is, but you're not exploiting it in any way. But now with univalence, we're able to exploit that additional structure. Okay, so it really becomes non-degenerate. Okay, so that's the idea there. We did that right. Okay. All right, so now, good, but I'm going to go, before I push further, so what's going to happen, all right, so to come, and then I'll show you, I'm going to get there. So I'm going to identify is set of A is going to be identified with, the idea is a zero type. That's what's going to happen. And the next thing that comes up is groupoid of A, and that's going to emerge as is a one type of A. And then there's a notion of a two groupoid. Of course, we start running out of words, so you start saying two groupoid, and then that will end up meaning is a two type. I'll explain what that is, and these will go to unboundedly, so they'll go for any n. So this is our first sort of, this is the first peak. So this is what I mean by the homotopy n types for n bigger than or equal to 0. I haven't really defined what is a one type. Well, what it means is you just go up a level and then you have a set. So having a set means that there's only two proofs there's only one proof that any two elements are equal up to higher homotopy. To be a one type means shift that whole thing up a level. It means that the identity space of the type is a set, which means that there are only one homotopy between any two paths. Okay, that's the idea. And to be a two type means you just keep bumping that up. Okay, so that's how the structure goes. You should not get the impression that every type is an n type for some n. Okay, that's not the case. Okay, but we can say that there are things that are n types. That is, are like this, okay? And I'll justify that later. I'm not going to do everything now. It's going to turn out that these are cumulative. Everything that's a zero type is a one type. Everything that's a one type is a two type, etc. So we're going to do that. And we're going to say something about what happens is when I say that something is a two type, there's an implication that it's not something high. I can also specify what it means to not be something higher than that. So it will not be higher than that. Okay, that's the idea. And so I'll show you how to do that. But before I do that, I instead want to work in the opposite direction. You would think, how can I work in the opposite direction? So what I want to do is I'm actually going to wind up defining this for n bigger than or equal to minus 2. Okay, and so I'm going to do the negative numbers first, but there are only two negative numbers. And the reason for this is it's a terminological clash. There were traditions of numberings, and somebody had to give. Okay, there was no way that we could each, start with 0. That wasn't going to work. So we ended up settling on the idea that we'll start with negative 2. So what I'm going to do is to get to there, I want to define another notion, and this one. So the definition is going to be this. We say a type A, and this really grates on my nerves, but it's the terminology. So a type A is, well, it's sometimes called an H proposition. That one, an H prop, and now this is what I really don't like, or just a prop. If and only if, for every x, y in A, theta x, y. So we can define this to be is prop of A is that type. That's what I'm doing. So what it says is that it's basically a sub-singleton. Another way of saying it is it's a sub-singleton, which is a way of saying is has at most one element. Has at most one element, but be careful. At most one always means up to higher homotopy. Meaning that there's a path between them. So you have to be careful of what you mean when you say at most one. So I mean is, if you give me 2, I'll show you a path between them. That's what isprop provides a witness to that. Okay? So it's a sub-singleton. So it's become more or less customary to call that a prop or an H prop, which I really hate. Okay, so this is a terminological. It's one of these terminological snafus. It's inevitable. We have two previously disparate communities and ways of thinking. We've realized that there's a lot of commonality. So of course we're going to have words that don't match up. So that's okay. That's just the way it is. But let me just explain why I don't like it. All right. The reason I don't like it is because it flies directly into the thing that I care most about in the whole world in my academic life is the idea is that propositions are types. Okay, so I'll write but. So to me, a proposition is a type. It's an attitude that you have toward a type. I've mentioned that many times. Sometimes we have the attitude toward a type that it's a data structure, and sometimes we have the attitude toward a type that it's a proposition because of psychological reasons. Okay, that's all. All right, but there's no actual difference. So from that point of view, you have no business distinguishing types that are props. Okay, and that's really annoying. Okay, all right. So I've vented my spleen now. So I don't like this terminology, but it's the way it is. So now we'll go with it. So okay. So why do I object to it so vehemently? Well, the idea is, in my mind, it's a holdover from classical reasoning, which I'm going to justify now, okay, in a particular way that you might find interesting. Okay, it's a holdover from classical reasoning that really goes back to Brouwer. Okay, and I'm going to explain this. Because saying that something is a proposition, we'll use this idea of a proposition, it means it has at most one element. Skates really close to saying either a proposition is true or it's not. But it doesn't say that, okay? It doesn't postulate the law of the excluded middle. It just says the truth of the proposition is it's proof irrelevant, okay? So what it is it expresses the idea, what is called proof irrelevance. For types that are called props. In other words, we call things props exactly when they're proof irrelevant. And that completely flies in the face of constructivism because the whole point of constructivism is that proofs are not irrelevant. In fact, the whole point of homotopy type theory is that proofs are not irrelevant. Proofs of identity are paths and so on, everything we've been talking about. Okay, but anyway, but this is where it comes from. It's proof irrelevant. So I feel one way to think about it, and I'm going to show you a different way to think about it. And one way to think about it is that it's a holdover from classical reasoning, that the proof never matters. All you care is there exists one or not. But you must be careful with those or nots because we're not postulating excluded middle. Okay, but that's the idea. So where does this idea of proof irrelevance come up? Well, even in a computer science setting, so historically, historically, Brouwer discussed this point at great length. In fact, one could say that the whole foundation of constructivity was an analysis of the implicit reliance on proof irrelevance in classical logic and criticizing that, because Brouwer was emphasized the idea of constructive existence or the constructive disjunction which should reveal the witness. Okay, that was in a nutshell oversimplifying Brouwer's critique of classical logic, was that it was neglecting the relevance of proofs. So of course historically it all goes back to Brouwer. But I'll give you a CS example which goes back to New Pearl a long time ago, which is we were thinking of, so we want to think of types as specs. And therefore we want to think of the terms or the proofs. These are types which are propositions, well, in the props as type sense. Okay, and we can think of proofs as programs that meet those specs. So that was the old idea. Okay, so initially when we were doing this 30-something years ago, in the early 80s, then that was the framework we were thinking of. So one of the first things you come up with is you say, well, okay, this is the amusing part. So I want to write down the function that, given a sequence, a finite sequence of natural numbers, finds the index of the first zero. So what you do, well, first of all, you have to say, so I have to have an input and I have to have an output, right, in some way, all right? So the idea is, what I'm going to do is I'm going to take, okay, really this is going to be a pi. So we're going to take in a sequence, okay, we'll call it S, all right, and then what we're going to do is we're going to find an I in N, or let's say I in the interval between 0 and the size of S, -1 or however you'd like to notate that. Okay, such that, okay, essentially S of I is equal to 0. And this would be in the natural numbers, nat, right, like that. So the spec is going to be, give me a sequence, I'll explain what this is in a minute, okay, and produce, all right, an I for which it's 0. So you already know what you're going to do. But we want a total function, okay? This is a total function. So we have to give you a sequence that actually has a 0. Okay? So this is in, let's call them T's, just to not confuse them. This is the things from, let us say, well, I could first of all say they're infinite sequences, okay, from nat to nat, such that, okay, well, let's just say there is an I in T, there is an I in nat, such that T of I is equal to 0, approximately, okay? So give me what in principle is an infinite sequence that actually has a 0, find the 0. And you could even beef this up and say an addition such that for every j less than I, S of j is not 0 maybe. You could put the spec in there if you like, okay? Put it in like that. Okay, so that's going to change things, but right now I want to just write the simplest possible form, okay, like that. And of course, if you write this specification has a solution which runs in constant time. Okay, because you tell it as part of the input in a constructive setting, okay, that there is an I at which it's 0, so I'll just return that I. So this has a constant time algorithm. If you think of the solution as a program satisfying that spec, that's a constant time solution, which we didn't mean at all. And yet, if you look in like an elementary textbook, that spec comes up all the time. So what went wrong? Okay, so do you see my point? Okay, clearly we had in mind we were going to like just go one by one, right, and iterate through this thing and have a thing that would take, you know. Okay, so a kind of linear time thing. So what went wrong? Well, what went wrong is that we provided too much information on the input. Because in a constructive setting, well, we really wanted this sigma on the output in a constructive setting because we want to say, look, we're programmers. It's no use telling me that an I can't fail to exist. I want you to tell me the I, okay? That's what I want, okay? So I write that. But on the input side, I didn't really mean what I wrote. Okay, that there exists, I meant something weaker, okay? And so the question is, how do you weaken it? So the issue is, so the problem is, in this sense, the problem is proof relevance. So that's the problem. Proofs are relevant in a purely constructive setting, so the input to S must reveal the answer that you're trying to find, and so the whole thing didn't exactly work. So what do we do? So the question is how to suppress. How do you suppress information in a type? And I'm going to tell you historically what we did, and then I'll tell you what we do now these days, okay? So how do we suppress information in a type? So the first idea was this, okay? So the first idea is an observation of Brouwer. Okay, so what is Brouwer's idea? Okay, is you change the spec to you use double negation. And you change the spec so that you say, there are different ways of doing this, but essentially what you do is you put not up here. Because now the assumption is, if there can't fail to exist an I, then there must be an I. Okay? Now this brings up another foundational issue. So someone besides Ulrich will smell what might smell what I'm alluding to here. Okay? Which is, if you think of this as that there can't fail to exist a point where it's 0, and it's an infinite sequence. Another way to pose this problem is I give you a bound a priori, and then none of what I'm going to discuss comes up, okay? But let's say we do it for an infinite sequence. So we say there can't fail to exist a spot in which is 0, That's what this is saying. Okay? And then I want to say find a spot at which it is 0. So how am I going to do that? Well, if it's an infinite sequence, and I know that there can't fail to be a spot at which it's 0, if I just do a while loop, essentially, and recur, it must terminate, shouldn't it? Maybe? Okay. Anyone, does this ring any bells? Ulrich perfectly well knows what I'm talking about, but does it ring any bells? Okay, well, in this particular setting, it's something called Markov's principle. If I put it as in this, it can be expressed, this is an instance of Markov's principle. Markov's principle says, a machine that can't fail to halt must halt. You can phrase it in different ways in terms of sigma 1 sentences and so on. It's all the same thing, okay? So let me say it again. If you can prove that a machine can't fail to halt, then it must halt. In a constructive setting, that's a very contentful statement because it's claiming you can extract the witness. When a machine halts in a constructive sense, it means there exists a number of steps at which if I run it in that number of steps, it will stop. Okay, that's a very positive statement. If you say to me, there can't fail to exist such a number, well, how are you going to find it? So Markov's principle postulates as an axiom that if you do the search procedure under the condition that it can't fail to halt, then it will halt, and you can write down the code using an unbounded loop. Okay, so that's the notion of Markov's principle. So this is the notion. So this is characteristic, you can guess from the name. This is the characteristic feature of what is called the Russian school of constructivism, which is people like Markov and Kolmogorov and a name I'm blanking on at the moment, but it'll come back to me in a minute. So this is called the Russian school of constructivism. Okay, Russian school, or people like Mintz and so on. Okay, so there's a Russian school of constructivism, takes Markov's principle as a basic principle. So in setting like New Perl, we didn't have Markov's principle. So actually this would have been stated as, instead of nat arrow nat, we would have a finite sequence of some length k. So we'd have a k here, sigma k, so that you know the bound. And then the bound, then you know in advance it's going to halt because you know the k. And then there's no issue. But I thought for fun I would bring up this issue of Markov's principle. Okay, so this is another one of those sort of axioms of constructivity that people sometimes consider. Okay, but what I want to focus on, in any case, independently of the side remarks about Markov's principle, is Brouwer's idea of double negation. And the idea is that double negation kills computational content. Or, well, which is, the proof relevance, the proof structure. So in New Perl, we referred to the computational content of proofs. So that's the structure of proof, so the proof relevance, okay? So double negation kills the computational content, and I can actually prove that, okay? It's very easy, okay? For any type A, is prop not A, where this is defined as not, well, write it out, A arrow 0, arrow 0. Okay, we can prove that, so that's a fact. So in fact, so Brouwer's point, so an example of Brouwer's point was then, and then he noticed the following thing, and then this comes up. So an example is, for doubly negated proposition, oh, is that true actually? Let's see if I wrote that down or not. Now I can't remember. Or is it the case? Excluded middle holds for doubly negated propositions?
Well, sort of the double negation of the excluded middle holds.
Yeah, that's what I'm saying. For doubly negated propositions, excluded middle holds, yeah?
No.
No, oh, it's not true. Okay. I almost said that. Double, yeah, okay, all right. I'm going to get to that. Okay, all right. Now I know that. Okay, all right. So let me skip that example. I hesitated for a minute. Okay. So the idea is that it kills the computational content. So you can just check this. So let's just check this. It's a very simple exercise. You just use an abort. It's a very simple thing to do here. So you can show that. So this together with one additional thing that, like, let's look at just propositional logic, led to what is called Gödel's double negation translation. And Gödel's idea was to embed classical into constructive logic. And it really involves kind of two related or two separate ideas that are kind of related, and I'll do it like this, okay? So it tells us that constructive logic is the master logic because classical logic is just a mode of use of constructive logic. So this pattern comes up again and again in computer science, and many of you know that I'm always like getting annoyed about these things because people fail to understand that by imposing more restrictions, it gives me greater freedom, not less, because I can relax them selectively. Okay? So it seems like constructive logic is a restriction of classical logic, and then we can moan and groan all day about our heterogeneous lists and some other nonsense, when in fact what is going on is you have something that is more expressive because I can get the less restrictive thing as a special case of it. So the interpretation is, for propositional case, is you interpret, there's various versions of it, but I'll do it like this. So this is called squashing with a trick, okay? So we'll call this squashing. So the idea is that I'm going to define this squashing, and I'm going to define it like this. So for A and B, you take the two parts and you squash them. But then what you do for the positives is where the action is. So what you do is, to recover classical reasoning, you have to do two things. You have to suppress the computational content. So with 0, you can define it to be 0, but that's because not 0 turns out to be logically equivalent to 0. So you can check that. In some sense, I ought to say not 0 here. And the reason you'll see why I ought to say that is, for disjunction, you double negate. To suppress, so this is the squashing. So if this is the nullary disjunction, I really should put not 0 here, but it doesn't matter. Okay, because 0 is degenerate. So you put a not here. And then, for implication, you need another trick. So if all I was interested in is squashing, if all I wanted to do is suppress computational content, so if we say just squash, then I would just let it glide here and define it like that, or arrow, or yeah, whatever notation I'm using on the right here. Okay, so that's for just squashing. Okay, I just want to squash them out. Because if you think about it, if this has at most one element, then this has at most one element. Okay, that's the idea. But if you want to recover classical logic, you need another trick. And the other trick is you put a not here. And this is for classical logic. And why is that? Well, one way to see it, without doing the whole proof, one way to see it is that you can say that classical logic is, for propositional logic, is constructive plus what is called double negation elimination, which says that not A implies A. So if you look at that formula under squashing, okay, and you work out what it should be, this will end up being, if you only do the first thing, its squash will be itself, well, that's assuming A is some atom, and we can just leave it like that. We don't want that. But if I do it in the second case, so this is case number 1, but if I do it in the second case, then what do I get? Not A implies not A, and that is realized by the identity. And this form, as many of you know, is called the CPS transform for compilers, under the interpretation that not A corresponds to continuations that accept an A. So what this is saying in particular, if you look here, A arrow not A, so that's B arrow 0, or B cont arrow 0. So let's curry that. So that's A cross B arrow 0 arrow 0. So what does it tell us? That a call site for a function consists of an argument and a return address. And you never return. So if you look at machine instructions, that's exactly what you do. How do you do a jump subroutine? What you do is you push a return address onto stack, let us say. You have an argument in a register, let us say, and you jump forever. The jump never returns. It's just that you pass enough information to the subroutine so that it knows how to do what you instruct it to do afterward, which is typically the next instruction, but doesn't have to be. So this is exactly what goes on in a computer, in actual hardware. This jump subroutine is a jump. It never returns. It's an unconditional jump that provides you a way to get back, which is a continuation. So this is the continuation transform. That's why I chose this particular one, okay, for what is going on here. Okay? So if you choose it this way, then you can embed, I'm not going to do the proof, everything that is true classically, including a particular double negation elimination, turns into a proof constructively. So it's telling us that constructive logic is much more powerful than classical logic. If you wish to live in the squalor of classical logic, then you can do that. You just double negate, translate everything, and then you can live in that little mess there with no proof relevance. But if you have no proof relevance to begin with, you can never recover it. There's no there's no way to say, take a proof irrelevant logic and somehow extract the proofs. Okay, you can't do that. You've already gotten yourself totally screwed. You're snookered. You can't get out of that game. So the right thing to do is to make the distinction and then selectively suppress it. Exactly like static and dynamic typing, so-called. Okay, it's another fallacy of the same character. Okay, and so this is the more powerful framework, the more expressive framework, okay, for that reason. Okay, so this is the first idea of sort of squashing and the idea of what it is to be a prop, okay? Good. Now I want to do another thing before we finish today. Okay, so what we did then, going back, is when we were looking at types of specs, is we were using double negation, okay, as a means of suppressing proof information because doubly negated propositions are, well, doubly negated types are propositions, let's put it that way, in the sense of being sub-singletons. Okay, so that's that terminological thing. Okay, so we're just going to have to get used to that. Okay, so that's the this is the critical fact. So you can check that. So that's very, very important. So I'm successfully squashing out, as we call it. So we called, so eventually what we did, by the way, and I'm going to come back to that in a moment, is we eventually defined, so at first we did Brouwer's idea, but the second idea, which is in some way a little better, because the double negation brings in, well, for example, it makes it possible to embed classical logic, so there's something more going on there. The second idea is to do an abstract notion of squashing. And that's what we're actually going to do momentarily when I talk about truncation. So in new Perl it was called squashing, in HOD it's called truncation, or propositional truncation. And you can think of it as the idea is you quotient by the full relation. In other words, you take a type, you take any two pair, you make a relation in which you say any two pair of elements are deemed equal. That's an equivalence relation. You form its quotient. That's one way to do it in new Perl. You quotient by the full relation. The other thing you can do is you can form a sub-singleton. You can look at the set of all star such that A holds. If you have this notion of set comprehension as an independent notion. So here I have to have a notion of quotient already. Here I have to have, a notion of a set comprehension. But if I have those around, then I can, another way to do proof irrelevance is you say it's the type whose sole element is star at most, provided that A holds. So those are two ways in which we did squashing in new Perl. And in fact, what ended up happening is these got coalesced into one thing, which was a quotient of a subset. Okay, so it's a PER. It's a partial quotient. You take a type and you quotient it by a symmetric intransitive relation, and the elements are the places in which it happens to be reflexive. And so that can consolidate those two. So in New Perl, we had this idea of a subquotient or something like that. I don't know what the right word is. Okay, was introduced that. However, that's an idea that only works well if you have a set theory, because it has to do with the proof relevance of equivalence relations, which we'll get back to in a minute. Okay, so we'll come back to that later. But anyway, that was the second idea. Okay, and what we're going to do in HOT is a version of this. Okay, a version. You could call it quotienting. It's a little risky because the situation is actually more complicated than that. But it's a lot like, it's kind of quotienting. You can say it like that. Okay, so now what I want to do is this. The next thing I want to do is talk about something which is very useful, which is called Hedberg's theorem, which is a convenient way of proving that something is a set. Okay? So it says a type with decidable equality is a set. So in other words, let's write that out. What does that mean? It says if for every x, y, and a, either you have a path between x and y or you don't. Remember, this means id a, x, y, arrow 0. So it's a positive information. I can either affirm it by showing it to you, or I can refute it by transforming the supposition into an element of the empty type. Okay? If that's the case, then is set of A. Okay, I don't know if I'll finish the proof today, so let me just sketch it, okay, and then I'll pick it up next time. This involves more of these iterated identity types. It starts to get a little hairy, so that's why I don't want to rush it, because you'll just say, oh, whatever. So I'll do it. So let me tell you how we're going to break this thing down, okay? So the first thing, so the proof works in two things. So the idea is, if you have a decision procedure for equality, then you're talking about a set. So in particular, you will not have a decision procedure for the universe, for equality in the universe, in the presence of univalence. Because, after all, it should make sense. You would have to find an equivalence, and that can be an arbitrarily subtle thing to discover an equivalence. That's not a proof, but it's an inkling as to why you should be able to prove that. Okay, but the idea is that if you do have a decision procedure, which you don't always have. See, in classical logic, you always have this. So notice a corollary, before I do that. Corollary, classical logic ruins the homotopy interpretation. I'll just write it this way. Classical logic destroys the higher homotopy structure. There are no levels. If you just, as a blanket condition, postulate the law of the excluded middle, then in particular you're saying every type has decidable equality, which means that in particular you're saying every type is a set, which means all this business about H levels, you can forget, it's gone, blown away. So what this tells us, now this is the personal irony. John, my friend and flatmate, who thought I was completely crazy talking about constructive mathematics, it turns out his whole career depends on constructive mathematics. That's the way I would say it, but that's like just to be annoying. Because, you see, if you take classical logic in the setting that we're doing with homotopy type theory, you can't do homotopy theory. So he would cease to exist. So I can get him back now, okay? So that's my thing. So here's what we do. Okay. So what we do is we do two things. We say, and then I'll stop here. So what we'll say is that decidable equality, and this involves a general thing that goes back to Brouwer, implies what is called stable equality. Stable equality says if there can't fail to exist a path, then there exists a path. That's what stable means. Stable equality means for A, right? Okay. So decidable equality gives you stable equality, and stability of equality implies sethood, right? That's the way in which the proof will go. This goes back to Brouwer. So I'm going to show you a couple of little derivations in logic that go back to Brouwer, which relate stability to decidability. Okay, so it relates kind of double the CPS transform to decision procedures, you might say, in a certain way. So stability, decidability implies stability, and then stability gives a sethood. So what does that mean? We're going to end up proving that something is not a set, and then apply effectively not existing a path, and then we'll apply stability to get a path out, okay? And we'll be able to get that because we know that it's decidable, and that will give us stability. So that's the outline of the argument. I'll show it next time. It involves a lot of scribbling. You can see I made a lot of mistakes before I got it right. So I want to make sure that I do it properly when I do it next time. So I'll pick that up next time, okay? And this will be I like it for two reasons. One is that it's a convenient way to show that something is a set, and the other is because it shows how centrally important constructivity is to the whole enterprise. And then what we'll talk about is truncation, the squashing, and then we'll revisit some of these principles like excluded middle and axiom of choice in the light of this notion of propositional truncation. And then it becomes a very interesting discussion will arise there. So I'm setting us up for that discussion. So that's what I'm doing. So we'll pick that up next time. Okay? Thanks.